Alright, so in this video I'm going to discuss the Feynman-Hellmann theorem for the time-independent Hamiltonians. So the theorem basically relates the derivative of the total energy of our system with respect to a parameter, namely lambda, to the expectation value of the derivative of the Hamiltonian of the system with respect to that same parameter, lambda. So mathematically speaking, the theorem states as following. It is the derivative of E lambda over with respect to lambda equals the expectation value in psi lambda of our Hamiltonian, the derivative of the Hamiltonian with respect to lambda, psi lambda. Alright, so note that here the lambda is a continuous parameter. And we're going to prove this theorem, but to prove the theorem we may need some things that are the following. Recall that our wave functions must be normalized What that means is that the inner product of my psi lambda must be equal to 1. Also remember that when my Hamiltonian operator acts on a state psi, it returns with the energy eigenvalue and the state psi. So with this in mind, let's go further to prove our theorem. So to prove the theorem, remember that this theorem stated on the left hand side that it is the derivative of my E lambda with respect to lambda. Now also remember that what is my E lambda? E lambda is simply the expectation value in psi lambda of my Hamiltonian operator as such. So let's simply apply the derivative operator to this E lambda, and I'll do that over here. That it will be simply equal to d over d lambda psi lambda Hamiltonian psi lambda. Now let's go further and distribute this derivative. This is some algebra. D psi lambda over d lambda Hamiltonian psi lambda plus psi lambda Hamiltonian d psi lambda over d lambda, and finally final term psi lambda, the derivative acts on the operator psi lambda. Alright, let's go another further step, but before we do that, remember this equation over here that we just wrote, and also remember that when my H acts on my psi lambda, it returns a constant energy eigenvalue and my state psi lambda. So if E lambda is a constant, I can write it outside in the following manner. I can write it as E lambda d psi lambda over d lambda, and the state psi lambda as it returns me, plus similarly again e lambda psi lambda and d psi lambda over d lambda, and finally the final term, that is derivative acting on the operator d Hamiltonian d lambda psi lambda. Alright, what can we do next? We can take the E lambda energy eigenvalue as a constant outside, and we can close the derivative. So closing the derivative in the following manner, d over d lambda returns us with this thing over here. And not to forget our final term, the very useful term in fact, psi lambda dh over d lambda psi lambda. Alright, now remember that our wave functions are normalized, and if they're normalized, then this inner product over here is equal to 1. And if this inner product is equal to 1, then the derivative with respect to lambda of a constant is simply 0. It vanishes. And if that vanishes, this whole first term over here will vanish. And I'll only be left with this second term over here. And remember, what did we have on our left hand side of the equal to was d e lambda over d lambda, which is now equal to this expression over here, that is psi lambda dh over d lambda psi lambda. Now if you remember from our first page, we stated the theorem over here, and this is exactly equal to what we have just derived over here, or just proved over here. So we have essentially proved our theorem in a very brief manner. Now, why do we use this theorem? What's the use for it? Well, the theorem basically allows us to calculate all of the forces in our system using classical electrostatics. Once the spatial distribution of the electrons or the charges has been determined, which is done by simply solving our Schrödinger equation for the system. Moreover, it is useful in computing or calculating the intermolecular forces in molecules, and it is very useful in computing the expectation values, namely the expectation value of 1 over r squared for hydrogen-like atoms. Now, this is for the time-independent wave functions. We also have the theorem for time-dependent wave functions, and if you would like for me to discuss the time-dependent wave functions, the Feynman-Hellmann theorem for those, please mention in the discussion box below. And if this video aided you in any sort of manner, please like the video and consider subscribing. Thank you.